All right, well, we've given everyone an extra minute since it's coffee break, but I think we better get started. I don't want to run too far over time. So, oh dear. Is my mic off? Nope. Hey, good now? Okay, sorry about that. All right, well, hopefully now that I'm talking, people will realize the coffee break's over and start trickling in more. So, I'm so excited to be here. Good afternoon at CephLicon. My name is Greg. I've been working on Ceph since 2009, 10 years on the beginning of next month, which is super crazy for me. Right now I'm on this RADOS team and working on some testing stuff, but once upon a time, this talk came out of from when I was the CephFS tech lead, and one of the things that we talk about a lot in the dev team, but don't really talk about for users or for other people in a lot of organized contexts that I wanted to shed some light on. So we're here today to talk about CAPS. CephFS file system inode capabilities. So we're going to real quickly go over CephFS and file system structures, although you probably already know all about that. Look at why we need to do locking for coherency, what CAPS are and what they mean, how the MDS governs them, and some of the consequences of those that you might see when running a Ceph cluster. So presumably you already know a Ceph cluster or a CephFS cluster will have monitors and OSD storing data and MDSs, and the client that's running and mounts CephFS will send metadata updates and requests to the metadata servers and send data requests directly out to all the OSDs. Nice split responsibilities, super scalable, super awesome. Within the file system, as in any other file system, you have directories, and those directories contain de-entry file names, and those de-entries are linked to particular inodes. In CephFS itself, the inodes are stored, the inodes and the de-entries are actually stored together within directory RADOS objects as part of the OMAP key value store. And the file data is stored as a separate series of RADOS objects based on the inode number of the file in question. So, CephFS is coherent because it's very important that file systems be coherent, especially if you want to say that you're a POSIX file system, which we do. And one of the things about a POSIX file system, a basic requirement, is that if you issue a write call on a file and that write call finishes, and then you issue a read on that file, that you get back the data you just wrote. And the fact that you're running on different clients, on different servers when you have a distributed file system, doesn't allow you to break that rule. If I have a client A writes a file foo and client B reads the file foo, it better get back the same data if the write call was done. And that means that we need some single authority on which we either explicitly or implicitly serialize all the operations, or at least linearize them down into a set of operations that we know are compatible with each other. And that means we need some kind of locking system. So in CephFS, the MDS is authoritative for metadata that it holds and that it shares out to clients. We have distributed locks running within a single MDS and across the MDS cluster that describe how the state that lock controls on the metadata can be accessed or changed. And then, in particular, and this is important, the MDS that is authoritative can issue capabilities or CAPS to clients that delegate some of that authority, so that if you have a client do a lookup and ask for a stat on a file, it can cache that stat and serve it again the next 10,000 times your really dumb process asks for it that second, rather than having to send a network round trip every time. There are similar solutions out in the wild, tons and tons of proprietary products in open source protocols. NFS delegations are coarser. You tend to get a read and a write on basically an entire file, but it allows the client to maintain ownership. And the Samba op locks, I haven't spent a great deal of time studying, but are pretty close to what we do. Quick aside, CephX caps are not what we're talking about here. If you're creating a keyring for a new client, and we also call those caps, I'm sorry, we're terrible at naming things. This was super bad of us, but we're talking about CephFS caps that are part of the client-server MDS protocol. So, there are a number of caps that a client can be issued by the MDS. The first one is a PIN cap, and within the, if you look at like MDS or client logging or Developer discussions will denote that with a lowercase p, and that's indicating that the inode exists. We have an auth cap for the authentication metadata around the mode and the UID and GID, which we denote with a capital A link cap, the linkage count on how many D entries are pointed at an inode, capital L, an XAdder, capital X, for the existence of XAdders and what their contents are, and then the file cap, capital F, that covers file data and the various timestamps and the file size. Within any given cap, there are several different or within every kind of cap, there are several different capability bits that they might have. You can have a shared cap, which generally means that you are one of many clients that has shared access to this state. Or you can have an exclusive cap. This is not like, you might have both, you might have neither, but these are two caps you can have. And if you have the exclusive cap, that means that you're the only one who has access to a piece of state. Like, okay, I have the exclusive auth cap, that means no one else has any idea what the auth cap looks like right now. There are some other caps you can have, though, on different kinds of locks. You can have a read cap, lowercase r, meaning that you can read it, a write cap, that you can write it, and then the slightly more powerful cache and buffer, meaning that you can cache reads or buffer writes. And I'm going through this quickly because we're about to go through them again very slowly. So don't worry if it doesn't quite make sense yet. And then there's one other special cap called lazy IO that I think came up in like a round table last night or something. I'm afraid we're not going to talk about that any more than just to know it exists. You won't see it unless you write custom software, but its main purpose is to let you skip a lot of the other cap handling. So not every cap actually uses every permission. Some of them are much more simpler than others, and some are pretty complicated. The pin one is just either present or not. If you have the pin bit on a cap on an inode, that means you're allowed to remember that the inode exists. Doesn't give you anything else, but you know that that inode exists, and it's called pin because if a client knows that an inode exists, the MDS has to pin that inode in its memory online cache. The auth, link, and XAdder caps can be either shared or exclusive. Those are the only two bits that they can be, and those mean some really simple but powerful things. If you have the shared cap on them, you can save the state locally and cache it and reference it, so that if you get a system call that says, hey, I want to do a stat, that says that you want to look at the mode and you have the auth cap, you can satisfy that locally without having to send a request round trip to the MDS. The exclusive cap is more powerful if it means that the MDS has delegated you full responsibility for owning that state. And it means that you can change the mode locally. If you get a system call to change the mode, you can just say, you can write it down in memory and say, yes, I've changed the mode, and then you can flush that mode change out to the metadata server at some later time. And that's nice because it means that you can make a lot of kinds of changes locally and reduce latency of operations and repeated lookups and requests. The file cap is the super weird powerful one. So the file cap covers more than the others. It covers both the actual file data, the ability to do reads and writes, and then the M time and the size, because and they're all smushed into the same cap, because if you do a write, you need to change the M time no matter what, and if you do a write or a read, you need to know what the size of the file is because you might be changing it, or you need to tell the system call, oh, the file doesn't exist at that offset or whatever else. So the shared and exclusive caps cover the timestamps and the size, and they cover those in the same way as the shared and exclusive caps do on auth or XAdder or link. They just are, if it's shared, I can look at it, and if it's exclusive, I can write it locally. Then the read cap means that you can read the file data, but it's not, but it's very specific. The read cap means that you are allowed to send requests off to the OSD to read data out of the OSD. You are not allowed to cache it with the read cap. You need the separate cache bit for that. So if you have a client, and the reason they're separated is because you might have another client that is doing writes. And so you need to know whether or not you're allowed to cache the data, or if that might make it inconsistent. Similarly, you have a write cap, which allows you to write the data synchronously to the OSD, but you cannot have, but you can't buffer the data unless you know that no one else is doing writes or reads, and so that's a separate bit in the system. Can I get someone to, does that make any sense? Anyone? Thumbs up, thumbs down? All right, Dan looks happy and no one else is angry at me, so that's good. Ooh, and I'm going a little faster than I thought I was, I think. All right. So the caps come from the MDS. The metadata server is the ultimate authority for all metadata. They get to decide who is allowed to do what. Within the MDS, each of those pieces of metadata we've talked about is controlled by a lock, its own internal lock that decides what kinds of state, or how that state can be manipulated by the MDS with the authority and other MDSs and other clients in the system. It's pretty complicated because you know, we allow clustered metadata servers, and so we do weird things like, say, we have a really hot read-only data set, so we're going to replicate it across the active set of MDSs and let them serve read-only data out of their own cache to all their clients. Or if we have, you know, 3 different active servers, even if they're not replicating data because it's hot, there are directory boundaries where one of them owns the directory, but a different server owns the inode that the directory is part of, and so they need to coordinate on that state boundary, and that means you need to be able to share different pieces of metadata back and forth to each other very carefully. And of course, it also controls which capabilities can be issued to which clients, because we need to make sure that only one client gets an exclusive bit, and that, you know, we can allow 3 clients to be writing at the same time, but if that's happening, none of them can have the buffer cap, and a reader who comes along needs to get the other clients to stop writing to make sure we get consistent read results back. And so clients send in general metadata updates and cap requests saying, hey, I've got this file open, so it would be great if you could give me the exclusive, or at least the shared bits on this file. And by the way, I need to change the M time because I just got a syscall setattr request. And within the MDS, there's just a big pile of heuristics that try and change the lock state based on all those inputs to optimize the system to behave well. I'm not going to walk through it, but this is the data structure that defines the lock states, which are all of these things, and then what the different MDSs, whether they're the ones in charge or not, and what the different are allowed to do, and what the different clients, what caps they're allowed to get on the file lock. I'm not going to walk through it in any more detail than that because we'd be here all day and I would tell a lot of lies because I didn't prepare enough for it. So caps can change, obviously. If you want to do a write and another client has the cache read bit, then those need to get then the client needs to drop those. And the MDS does this by sending out messages to clients either granting or revoking caps, usually because of some other client's activity, but maybe because the MDS needs to do something. When a client gets a revoke, the client has to stop using the cap, which is the client's responsibility, and then it needs to send the MDS a message acknowledging the change affirmatively. The MDS doesn't just get to assume I sent the message and so the client must be done now. It has to wait to get an answer back, because without that affirmative piece of knowledge transfer, maybe the client never got the cap change to begin with and is still continuing to serve reads locally or something. Now, stop using that state might be really easy or it might be really hard. If it's just a read cap or a shared cap on the mode, then you just forget what the mode is and drop the bit. And if you get a request for the mode, then you have to go to the MDS for it. But you might have 100 megabytes or 10 gigabytes of dirty file data that you've buffered up while writing that you need to flush out to the OSDs. And that can take a while. So just to illustrate this with a simple example, we've got here an MDS in the middle and 3 clients, and they're all doing work on one file, doing a lot of reads or something. And so, I'm not sure. Yeah, anyway. So they got a bunch of shared state and then the file read and write, and they've got a particular mode that they are aware of that is the mode on that file. And then one of them says, oh, I want to change the mode. And so he proactively drops his auth shared cap and he sends to the MDS, here's the new mode I want to set. And the MDS gets that request and says, oh, well, there's a bunch of people with auth shared, so they need to drop it before I can make a change. And he sends out to them a revoke auth shared message. Those clients get that. They knock out the auth shared bit locally and the mode that they know about, and they send back a message saying, okay, I've dropped it. Although, by the way, I'd like it back again, please. And then the MDS makes that mode change locally, sends out to the clients, hey, here's you can have the auth shared bit back with this new mode. And then when they received and processed that message, they integrate it into their cache and continue going on the way they were before. If you're trying to make a client drop a buffer, that was like one round trip each plus one around it from the client to from the initial client to the MDS. But if you had a buffer cap, you would also have a bunch of round trips out to OSDs, flushing out file data and stuff. Wow, I'm talking really fast. Any questions so far? I've actually got a mic here. If anyone's got something urgent, or we can wait to the end. All right, Dan. Shoot, I forgot to get a volunteer to run the mic around. You asked the first question, so you're getting drafted.
I volunteer. You said that it may happen that a buffered write cap can take a long time to flush. The client can take a while to flush the data. Is the MDS given some updated information from the client that I'm busy flushing data, please wait, don't ban me, something like this? Or is it just a
That's a great question, and we'll talk about banning in it later, and the answer is no. The MDS gets no update from the client saying that it's doing any work. It's just sort of that's not a system we've needed or tried to build in the past, so it just sort of sits there and waits until the caps come back.
Okay.
All right. So there's some consequences of the cap architecture that we've outlined here. First of all, the MDS has to remember everything the client has pinned, and that's because the client's doing something with it, and so and the MDS needs to remember, oh, these clients know about this file. So if client A has an inode pinned and client B comes in with an unlink to the inode, and the link count drops down to 0, we can queue the inode for deleting all the file data, but we can't actually get rid of it until no one else is has the inode open, because you're allowed to continue reading unlinked files until the last file handle closes. And so your MDS cache actually needs to be larger than your client caches, which sort of is obvious when you think about it, but is a thing that a lot of users have had trouble coming up with ahead of time, and that we haven't done a great job communicating. A 4 gigabyte MDS cache, when your clients have 256 gigs of RAM and are happy to keep 16 gigs of dirty metadata, is not going to work very well. And finally, because the caps are cooperative and the client needs to affirmatively tell the MDS that it's dropped caps, those clients need to work right, or access can be blocked to others until something happens to change the state external to the system. There are 2 big health warnings that come out of the cap system right now that people see sometimes and cause trouble and confused about. First of all, a client might be failing to respond to a capability release. This happens when the MDS has sent a revoke message out to the client, like the revoke AS example, but the client for some reason isn't returning the cap. Now that might happen because the network or OSDs are so busy that it's trying to flush out dirty data or do something, and it's just backed up and can't finish the stuff it actually legitimately has to do. It might be, we've seen sometimes in the past, that the MDS for some reason just revoked 2 million inodes worth of caps out from the client, and that takes a long time to flush back, and so it couldn't flush them all within the time window. It could be that there's a software bug and we messed up and the client is just broken. It could be, although this hasn't happened yet that I know of, that you let in some evil user and they wrote a custom client that was designed to break your system. Or there could be just something else making things slow. Maybe your the remote server got disconnected briefly, or whatever. By default, this message goes into the health alerting system after a client has failed to respond for 60 seconds. This will turn on. And there's one option which is off by default, which lets you forcibly disconnect clients which aren't responding, and would be the way to deal with software bugs or malicious clients or things. But we don't have it on by default. I didn't actually ask why the current thinking is, but generally it's because like things might just be slow and you don't want to boot out clients unless you really, really are sure you want to boot them, because they can have dirty state and you've lost updates that are supposed to be in the system. The second big health warning you can get is that a client is failing to respond to cache pressure. This happens because, as we examined, the MDS needs to keep cached everything that the clients know about. And so if it's using up more memory than it's supposed to or thinks it's about to be, it can go through and say, hey, I want all of the clients to drop 10% of their pin caps or something like that. And it'll send out a message to the client that says, hey, I don't care what it is, but you've got to drop some of your caps and tell me what you've dropped. And in this case, the client hasn't dropped enough quickly enough for the MDS to be satisfied, and so it starts warning through the monitor system. Now that could be, again, because the network and OSDs are so busy that it's just backed up trying to get rid of stuff. It could be that you have a software bug or malicious client, or, and this is a key one, your client might actually be using all the metadata that it's got pinned from the MDS, and it can't drop anymore because your application has 1 million open files, and the metadata server really only has enough memory, or the memory target on it is set for 800,000 open files, and so no one can fix that for you. You need to go and make configuration changes to the system. I can't tell you how quickly it comes up because it's a weird decay counter, but if you see this, you want to go and look at what's happening because it's a sign that there's probably an imbalance or else a misbehaving client for some other reason. So we do a lot of programming with caps if you work on the CephFS team, or coming soon, perhaps on other projects like an NFS or a Samba re-exporter. This is a very, very chopped up bit of the write call in the user space client library. So I've chopped off the front of it. Let's see, I think I can pull up a pointer here. There we go. Okay, so sort of the first interesting thing here you'll see is we have this get caps call, which I haven't shown because it's long and very nested. But we're passing into it that for the inode that we're working on, we definitely need the write cap because we're about to do a write. And also we need the auth shared cap because we need to check the mode and stuff and do permissions checking and stuff. And we would really want the buffer cap if we can have it. And then we have these other things. And that get caps function goes through and does a lot of complicated checking. But if you don't have the caps you need, it actually sends off a message to the MDS saying, hey, like, I need these caps, please. And then sleeps until you get an answer back and then returns. And either you succeeded or you failed. And if you failed, we return the error to the caller. Otherwise, we continue on. And then we do some cap checking, which I've elided here. But we put a cap reference, which the get caps function gave us, on the auth shared cap. And this is how we know when caps are in use or not. They just have a reference for, hey, I'm like, this cap is dirty. You can't or it's not dirty, but this cap is being used by a piece of code right now, so I can't drop it at the moment. Then we say, okay, if I have the buffer cap and what we call the object cacher is turned on, then I'm going to write into my local buffer rather than sending it off directly to the OSDs. So I'm going to get some cap refs for that, like, okay, now I'm using the buffer cap because I actually have buffered data, and I'm going to issue a write into the object cacher. And then, okay, now I've no longer got now I'm no longer using this buffer cap because the file write did its own accounting for that. And now I'm done, hooray. Or we didn't have the buffer cap, or we're not using the object cacher, and so we need to skip over that, do a direct write. So we issue this write via the filer, which actually goes out and sends messages out to the appropriate OSDs based on the I/O that we just got. And then we wait. We have this onFinish object, which we constructed right here. It's basically a condition variable, and we say, hey, like, and we pass that in. We say, all right, do our write, please send out all the messages I need. Oh, whoops. Please send out all the messages I need to the OSDs, issuing these writes. And now I'm going to sleep until the writes are done. And then when they are, hooray, commit the writes, do a bunch of cleanup, return back. There's a lot of this all over the client code because, you know, we need to check that we own the appropriate caps whenever we make use of them. If we don't own them, we need to go get them. We need to sleep while we wait for messages to come back. It's very exciting. A newer thing, this is a short set of functions which are available in the libCephFS user space library bindings. So Jeff Layton gave a talk with Patrick about using NFS Ganesha on top of CephFS to provide NFS exports to untrusted clients and things. And in NFS before, there's this concept of delegations where you can delegate to the client the authority to do read and writes locally. And we wanted to integrate that into CephFS so that we could run a CephFS system where we have some native CephFS clients and some Ganesh and some NFS some native CephFS clients and some NFS clients, and maintain cache coherency across all those sets of clients. And that means that if someone on NFS opens a file, we need to hold that file, those file capabilities, the entire time that the NFS client has them, even though the CephFS client that backs NFS might drop them. And so we have this thing here where the core of it is this CephLL delegation call, where we say, all right, on a Ceph mount, I want a delegation on a particular file handle, and it can be a read or a write delegation or drop my delegation. And I'm going to give you this callback for when you need to tell me to drop the delegation. And so then the client goes and tries to get all the caps you need for a read or a write delegation. And if it fails, it says, sorry, and the NFS server just has to give up. But if it succeeds, it says, all right, I've given you the delegation. I'm holding all the caps for you. And if I get a cap revoke that would require dropping the delegation, I'm going to signal you via the callback that you passed in that you need to drop the caps, or that you need to revoke the delegation to your client and tell me when you're done, so that then I can drop the caps and continue on. Because the NFS delegations are a little weaker, or are a little less fine-grained, and this is a pretty simple interface, we hope to extend it into something that works for Samba op blocks and various other file systems in the future. But it sort of outlines the model for how we can expose those out to the world in a way where, if you at least trust your re-exporter a bit, that they aren't going to break too badly, you can maintain cache coherency across protocols without delving too deeply into the CephFS internals on your own. And that is actually all I got, so we've got plenty of time for questions if there are any, or for you all to sit quietly and absorb me talking too fast if not. And otherwise, thanks very much. Any questions? Raise your hand.
Is there any kind of support for multiple clients getting access to write on the same file?
Is there is there support for multiple clients to write on the same file?
Yeah.
Yes. Yes, you can have multiple clients write to a file on the same time. If anyone wants to read, then they're going to need to trade back and forth to maintain the ordering. But multiple clients writing is really easy.
This might not be related to caps, although I'm not sure. Like, are caps involved in any sort of locking when you have multiple writers? Does POSIX guarantee that you have like atomic updates to blocks or something like that?
Okay, so if you have a write that crosses RADOS object boundaries, then no. They can actually get split, which strictly speaking is illegal, but is a very, very rare circumstance. So we mostly allowed it right now. But you're right, that is a cheat, and we're terrible. And the person right behind you.
Can I just check I understood correctly? So if you've got a client that's got the buffered write cap, and the metadata server says to it, give me that back, and then the client crashes, are you then stuck?
You are stuck until the MDS server decides the client actually crashed and died. So separate from the thing, like we have the timeouts where we evict you that I said are turned off by default, but if the session, like the TCP session goes away, there's a timeout there where it says, okay, no, it's gone, and boots it. But you do have to wait through that, because otherwise, like if you do like it's an eviction, you know you lost dirty state, and like that's really bad. There's not really like mostly because no one's really developed good rules around it. Like POSIX was written for local file systems, and if you crash in a local file system, it's because like everything went kablooey and the server has to restart anyway, whereas for this you don't. So we try not to evict clients, but yeah, we will eventually.
For the write caps, is there a way to like just get a write cap for a certain range? And sorry, I might have missed that.
That's a great question. So there are other file systems that, yes, issue, they're generally called file range, file range locks or whatever, except that's the F-control one, whatever the functional ones. So no, in CephFS, a read or a write cap applies to the entire file right now, and so you can't issue them to specific ranges. That's an extension that many years ago we've talked about, but so far it hasn't come up because it's mostly of interest to supercomputing people who wrote things tuned for luster. And the community is focused on other kinds of stability, and no one's paid a vendor enough to make it worth their while yet.
What can happen if you set like blacklist client on eviction to false?
Okay, so yeah, we evict clients if they hit too many timeouts or whatever, and by default I think by default we blacklist them, which means that they go into a thing called the blacklist in the OSD map that prevents OSDs from accepting any communication from those clients. If you turn off the blacklisting, a client can be evicted from the MDS and lose all of its caps, but not have been told that yet, or be malicious or whatever, and send off reads and writes to the OSDs with the permissions they used to have, and because they have a direct data channel to the OSDs, their IO requests get serviced. We don't have any sort of request checking that between like any sort of side channel from the OSDs to the MDSs to make sure a client's allowed to do stuff. Because either we would need to, on every request, have the OSD ask the MDS if stuff's allowed, which is super slow and not scalable at all and terrible, or we would need to have some sort of like shared secure token between them, which is an interesting research project that I've thought about a little bit, but is definitely not a solved problem for systems like this.
Another question. Do idle clients like decay the caps that they have if they're just not doing anything?
So it depends on the version you have. Older versions of clients tended to keep everything they ever saw until they had a reason to get rid of it. But I believe in Mimic or Nautilus, they've started pruning rather more aggressively. That's something that is still being worked on from experience, because like it's good if the client knows as much as possible because it can answer questions really quickly, but you also have the trade-off of, okay, like maybe some other client is about to turn on and really wants all of that memory space on the MDS cache. All right, well in that case, I will be around all week if you have questions. Thanks very much for your time and attention. Enjoy the last couple talks of the conference.